Hello, my name is Maido and I am a materials scientist. Today's topic will be the scanning electron microscope, which is one of the most favorite and powerful tools used by many scientists all over the world. So first I will describe how it works and then I will show you how to operate one. In order to study and develop different new materials, it is needed to somehow see what is happening on the microscopic scale. And over here we have a modern optical microscope which greatly magnifies the surfaces which we are studying. But sadly this is sometimes not enough. So if we want to study really small things, then we should use electrons instead of photons. And the great thing about electrons is that they are very small and they also have negative charge, so it is easy to manipulate with them. So let's take a look at the most important components of the scanning electron microscope. On the image you can see the electron gun, which emits electrons. The anode, the lenses and the scanning coil are there to manipulate with these electrons. And also you can see on the image 3 detectors, which basically catch all the signals which are emitted by the sample as electrons interact with it. There are different types of electron guns, but in the case of older electron microscopes we are usually dealing with tungsten filament. This tungsten filament is heated up to 2400 degrees Celsius, where it starts emitting electrons. These electrons are now accelerated down the column by the help of this anode. And the accelerating potential can be from 1 to 30 kilovolts, which is selected by the microscope operator. The accelerated electrons are quite scattered, so the magnetic lenses focus them into a narrow electron beam. These lenses also control the amount of electrons which actually reach the sample. The scanning coil purpose is to make the electron beam move in such a way that it scans row by row across the surface which we are studying. The final focusing of the electron beam is done with the objective lens. Each point on the surface which is bombarded by the electrons is emitting different signals which are going into the detectors. And by using these signals we can create image of the surface. There are 3 basic types of signals which are being detected by the electron microscope. These are the secondary electrons, backscattered electrons and characteristic X-rays. These signals can come out from different depths based on their energy and nature. When the electrons of the primary electron beam interact with the sample, then some of the electrons from the sample can be kicked out. And these electrons are called secondary electrons. The secondary electrons have very low energy, so they can only escape the material from near the surface. And after they have escaped the material, they will start moving towards the collector, which has positive potential. And once they have passed the collector, they will interact with the detector behind it, which is called the secondary electron detector. And by using this signal, we can create a secondary electron image of the surface which we are studying.
The secondary electron images are black and white. The brightness of a surface detail on the image depends on the amount of electrons that has escaped it. The electron yield is larger on sharp protrusions, spherical areas and edges. However, deeper pits and holes will appear darker, as less electrons escape them.
Some of the electrons from the primary electron beam interact with the sample in such a way where they don't lose much energy. These electrons will go deeper into the sample and come out in a similar direction. And these electrons, which are backscattered, are collected then with the appropriate detector.
The electron yield for backscattered electrons depends greatly on the substrate atomic number. Surface details with larger atomic number than the surrounding matrix will appear brighter on the backscattered electron image.
When the primary beam electron's energy is sufficient, then it will excite the atom of the sample. And during the relaxation process, characteristic X-rays are generated. These X-rays are then collected with the EDX detector, and this allows to measure the composition of the sample. All these measurements are done in vacuum because we need clean surfaces, and we also do not want the electrons or the X-rays to interact with the gas in the chamber. So let's see how the real machine looks like. So this is the actual scanning electron microscope. As you can see, this is computer controlled, and it was bought for about 1 million euros. And with the maintenance, the price has doubled by now. And it will weigh about 1 ton or so. So it's a heavy machine. But let's see how the measurement is done. In this demonstration, we are going to study this piece of aluminum. It is aluminum alloy which is used in aircraft building. So let's see how it looks like. This sample is attached to a special holder with the help of this carbon tape, as you can see here. I will also scratch this sample, so if this alloy looks very boring, then we have at least this scratch to look at. There are two basic options to put the sample inside the microscope. We could use the main door, like this, then we would have to ventilate the whole chamber. But luckily, in the case of this microscope, we also have the small airlock, so we will use this one. The airlock was previously ventilated, so I can simply open it now. And I will put in the sample. As you can see, the sample is fixed inside, so I will close it. And now I will pump out the gas. So I have pumped out the gas, and now I have to put the sample inside the chamber, and I will do it with the help of this rod over here. So I will gently push it inside. Kigidigi. All right. Now I will pull it out. As you can see, we have very nice vacuum inside the chamber because we used the airlock, so we didn't waste any time pumping out the gas. And the first thing that we have to do here is move the sample under the electron column. And this microscope is quite easy. With just one click, it moves right under the column. No. The sample is now correctly positioned, so all that we need to do is activate the electron beam window and then turn on the beam. And as you can see, we have selected 10 kilowatts for the accelerating voltage, and this should be suitable for aluminum. And now I will unpause it, and can start studying this material. So I will enlarge it, scan a little bit slower, and play with the contrasts and brightness, and we can see the first image. We'll also try to focus it a little bit. And now we are ready to take the image. I will simply scan it very slowly. And after scanning, we can save the image. At the moment we can see the scratch which I made previously. Compared to other microscopes, the scanning process is actually quite fast. For example, in the case of atomic force microscope, you can wait 6 hours to get a similar image. And it may not always work. So the image is nearly done. And now we can save it. Let's see what else we can find on the sample surface. I can easily move around by just clicking with the mouse, and when I have found some interesting place, then I will simply zoom in by using just one button again. And over here you can see some bright spots on the surface. Scan a little bit slower, and because this is an aluminium alloy, and we have some metal faces in it, and as you can see, they look slightly different than the surrounding matrix. So this is one of these crystal faces. And such faces will give this alloy its mechanical strength. Okay, I will save the image again. And keep searching for interesting places to study. So this is the end of the scratch. Let's see what it looks like. I will turn down the brightness a little bit. You might get a better image. Now this image is done from the top view, but we can also tilt the sample a little bit. So let's try to tilt it for maybe 15 degrees. You can see that the sample is tilting. And let's see how the surface detail looks like now. As you can see, it looks slightly different. So when you do electron microscope studies, you sometimes want to tilt this sample to get better images. And when I'm done with measuring, I will tilt it back to 0 degrees. And turn off the electron beam, and now I can take off the sample. In order to take out the sample, I will need to pump out the gas from the airlock again, and then also move the sample into the correct position, so I can remove it with the rod. And now I will take out the sample again by using the rod. And now the sample is in the airlock again. So I will ventilate it. So we are just ventilating this small airlock here, not the whole chamber. It also takes less time, and we are wasting less gas. And we can now take out the sample. So, thanks for watching, and leave your comments below.